For this tutorial, we're going to introduce the concept of pulse width modulation, and we're going to use it to drive the piezo element speaker found in your Launchpad kit. So if you go ahead and remove that from the kit, it looks a little bit like this. On the back side, you'll notice a positive and negative lead. Now it doesn't quite matter which one you tie to ground and which one you tie to the signal wire. A piezo element speaker works by flipping to an up or down state, as opposed to a regular speaker which will follow a waveform depending on how much electricity you're putting to it. This one just goes to an up or down state, so it clicks back and forth. And if you do it fast enough, it will buzz. Go ahead and get your board out and run a wire from P1.6 to the breadboard and from ground to the breadboard. I'm going to go ahead and match the positive lead to the red wire and the negative lead to the black ground wire. Now, to use PWM on the MSP430, we need to introduce the concept of timers. To help us do this, I'm going to list some materials you should have going forward handy when you write code, because these pieces of reference are going to help you understand the way the MSP is constructed and how to write code for it. So one of the first documents you want is the MSP430G2553 header. This is the header that's included every time you compile a program for the MSP430. So if you search this document, you'll notice right here is our familiar watchdog timer control register, which corresponds to this constant, as well as a whole slew of other definitions, like our bit 1 to bit F here, which are handy for addressing different pins. It's an important document to have, and you should have it up almost all the time when you're coding for the MSP430. Another two documents you're going to want are the MSP430 Family Users Guide, which if you Google for SLAU144i.pdf, it should come right up, hosted on TI's website, as well as the MSP430G2553 datasheet. So this is the datasheet that is specific to the architecture we are using for the class. As you can see, here's a view of our actual package. We have a 20-pin device. As you can see here, there is a indicator for P1.6, and after the slash there is a TA 0.1. This indicates that this pin can be used as an output for timer A0 inside of the MSP430. To get this one, you can just Google MSP430G2553.pdf and it should come right up. Let's move on back to the user's guide and use it to look up how to do PWM on the MSP430. So searching that takes me to the timer A section. So this chapter talks all about how to use timer A, and I recommend reading this if you need further information. But a quick conceptual way to think about it is it's just a clock, like the 1 megahertz CPU clock, and we can use it to run different peripherals or to time different events. And you'll notice we have 2 or 3 configurable capture compare registers. Let's move down to past the block diagram to a good example diagram of how this will work when you use it. So here we go, there's an output example with the timer in up mode. In this mode, the timer will count up to the TA CCR value, which, as I said, stands for the capture compare register. And after it hits that, it's going to go back to 0. So as you can see in this figure, the timer is going to start counting from 0 here. It's going to go all the way up to TA CCR 0 and then reset. And it's just going to do this over and over forever. Now, this timer is running as fast as your CPU is, so since we're calibrated at 1 megahertz, the timer is adding 1 for every cycle, so that's 1 million times a second. We will be using output mode 4, which is just a simple toggle mode. So as you can see in this mode, this line right here for TACCR1 is the line, the limit, excuse me, that when the timer hits, it will toggle the voltage on pin 1.6. So we'll be counting all the way up to CCR 0, but every time it hits CCR 1, it will go ahead and toggle back and forth. The way that we're going to use TA CCR 1 is to just leave it undefined. So if you don't set it, then it will just be 0. So meaning every time that TA CCR 0 is hit and it flips back to 0, then output mode 4 will know to toggle that pin. So we don't need, that way we don't need to set TA CCR 1. We can just set the actual time to count up to, and it will just toggle each one of those times. So this might help if we actually write some code for an example. So notice we have our standard watchdog timer control, hold, and calibration to 1 megahertz. We've selected bit port 1.6 to be an output pin, and right here we've selected it for the special function, meaning it is now an output for timer A0. Without this, it won't be tied to the timer and nothing will happen. So now we just need to set up the timer the way that we want. So the first thing we'll do is set CCR 0 to a period that we want the PWM to happen at. Secondly, we will set the control to output mode 4 so that it knows just to toggle P1.6 every time CCR 1 is hit. Which again, this is at 0. Since we are not defining this register, it will just default to 0. So every time the timer is going to flip over, it's going to toggle the voltage, and you're going to get a waveform like this. Up and down a square wave like this. And the frequency of the square wave is determined by this TA0 CCR0 register. Finally, we can set the control of the timer. And to understand what these values mean, it's a good idea to go ahead and move to the header file. Let's search for testcell_1. We're using 2. So this line right here, and it's commented, and it tells you that we are selecting the source to be the submaster clock. So the main clock here is running at 1 megahertz. If you don't set anything else up, the submaster clock is also going to run at 1 megahertz. So now this timer is going to add 1 for every CPU cycle, 1 million times a second. Since the timer can only count up to OXFFF, which is 65,535, that means it's going to flip pretty quickly. And in fact, it's going to flip even more quickly since we're only counting to 283 right here. So to combat that, we can use a divider, which is what we're doing right here with ID3. We're dividing the input by 8, meaning that instead of 1 million, we will be at, let's see, 125,000 every second. So that just slows down the timer a little bit to allow us to use it a little bit more easily. The final one is MC_0, which you can find right here. And this just tells it that we want up mode to CCR0, which was the way this one was set up for this example. There's another one called continuous up, which will count up all the way to FFFF, but we don't want that. We want to define the period for our square wave with CCR0. Finally, we'll want to just go ahead and move into low power mode. We used 4 in the last video with interrupts enabled. Unfortunately, that shuts down too many parts of the microcontroller. So for this, we can use LPM 1, and that's as low as we can go. If you go any lower, the submaster clock will be shut off, and that means this timer won't be able to source it and count. Alright, it looks like we're ready to go ahead and flash this to the board. I'm going to check my makefile that I have PWM defined, and I'll make flash. There you have it. You'll notice right here, since P1.6 also tied to the LED, you can see the LED is a little bit dimmer than it normally would be if you had just turned it on. You can hit reset to stop. It's also easy to just pull a pin if you don't want to hear it anymore. We can write some different values here, like 53. Or even, let's see, 190. So as you can see, this is an easy way to get some notes playing out of the speaker. If you wondered where I got these values, I am finding them on this website here for note frequencies. I just Google frequencies of notes. As you can see, A4 is 440 Hertz. So what you can do is take your 1 million cycles a second divided by our input divider, which we've set at 8, and divide it by the hertz of the note, which is 440. And you get the number you should count up to obtain that frequency. The -1 here is a convention that I've seen, meaning that since 0 and the ending number are included on the timer, this just makes it so that it counts to the expected number. So you could just write 284 here, or 283 to get 284, but a lot of people just by convention write -1 so that 0 is compensated for. I have a small demo here. If you spend some time moving all these frequencies maybe into a struct and then write a couple functions to play different notes, it's an easy way to just come up with a piece of music if you'd like. So we'll go ahead and flash this to the board. And there you go, just a way to get some sound out of your MSP 430.